the pressure actually drops, and that's what's going on inside this venturi. As the water, in this case not water, as the air speeds up, the pressure inside the ejector drops. And then, because there's another passageway into it, that outside air pressure is pushing its way in, because the air pressure inside is less than the air pressure outside, and so the higher pressure wins, so the air continues to go in through the vacuum port. Now, the pressure, the difference in pressure that we can generate with most of the standard type ejectors is roughly about -12 psi. So if the outside air pressure is around 14, 14.5, standard is 14.7 if you're at standard temperature and conditions, but say 14, 15, 14 and a half, that means that the pressure inside here has got to be somewhere around 2 to 2.5 psi. And so the difference between 2 psi and 14 psi then of course is 12. There's a -12 differential, and so that air is pushing its way in at -12 psi. So what that means is if I had a 1-inch cup, I could theoretically, this is not what I would do, but I could theoretically pick up a 12-pound piece, a work piece. Usually you don't want to go at the maximum of the capability. Normally you'd want to go a half, or even at least a half, probably a quarter. But anyway, theoretically I could lift 12 pounds. All right, so here's another example of a type of ejector, the ZU. This is another inline. But what I'm showing this one for is this one has what's called a single stage, meaning there's one place where the air can come in terms of a vacuum and make up the low pressure that you're generating. So what that means is since there's one passageway, it's called a single stage ejector, and in this case it'll run 20 to 30 liters per minute. But I want to show you, more importantly, not the statistics of this particular ejector, but if you'll notice, if the single stage is 20 to 30 liters per minute, a 2-stage or even a 3-stage, notice those numbers get to be a whole lot bigger. And the reason that can be a whole lot bigger is because there's more pathways for the air to come in and try to fill up the volume. And it's a larger ejector as well. So what that means is the faster that the air is trying to fill up this void, the faster the cup can absorb, that's the word used, when the cup is holding fast to the workpiece, the more flow, the faster it can do that. So if I have a single stage ejector and a double stage ejector hooked up exactly the same way, the double stage or the 3-stage ejector will grab a hold and be ready to move a little quicker than the single stage. So what that means is if you have a customer that's having a timing problem, that their cups aren't grabbing a hold, or again the word is adsorb, quickly enough, maybe you should talk to them about a 2-stage or a 3-stage ejector so it'll grab a little faster. They all generate about the same pressure differential, so you're not going to get more lifting force out of them, but you'll get a little more speed. And of course they come with different options with pressure switches on them and other things, but the main thing is the flow. Now another thing that you'll find on a lot of ejectors or vacuum generators is what's called a braking valve, or some people will call it a blow-off valve. What that means is not only will this ejector, this generator, create low pressure, which that's this part of the circuit there to the left. It goes through a little valve that opens and closes. It goes through the ejector. As the air goes through the ejector, it creates low pressure, goes through an internal filter, and grabs a hold of the vacuum pad. But not only will it do the negative pressure, or the low pressure, but it has another pathway for air to go through as just positive pressure. Now the reason you would have that is sometimes, especially in a quickly moving setup, you want that workpiece to be dropped down and then you want that cup to release very quickly. or if you have a workpiece that may have oils on it, that cup will try to stick to it. So what you do is you use what's called a blow-off or a braking valve to put positive pressure through the cup, meaning you're pushing the workpiece off of the cup with positive pressure rather than only just creating low pressure, which allows the cup and the workpiece to be pushed together. So if you hear anybody talk about they need an ejector with a blow-off, that's what they mean. There's actually two solenoids, usually two sets of wires to them that have that can either generate low pressure or will actually push positive pressure out through the vacuum pad, and that's for speed. Faster they want the cup to move back and forth and let loose of the workpiece, they might need a blow-off.
Excuse me, John.
Yes, ma'am.
We have a question.
Awesome.
So back to the previous slide. The question was, I've noticed line pressure, PSI, doesn't necessarily have to be high to be effective, but larger diameter air lines does improve vacuum due to increase of air volume through the ejector. Is that fact or fiction?
It certainly can be. I can absolutely agree that the more pressure you put to an ejector does not improve its performance. In fact, near the end of this presentation, I'll even show the slide that proves that. So yes, you are correct. More, the typical guy saying more pressure is not a great idea. In fact, it will degrade performance. And then the second point, larger tubing could be helpful if you've got too small a tubing to begin with, which is restricting flow, especially if you have a long run from the air source to the ejector of tubing. The longer the tubing, the more restrictive the airflow. Quite literally, the difference between a half-meter run of tubing versus a full meter of tubing is, 3 meters of tubing, you've actually reduced your flow of air through it by 50%. So yes, it's possible that tubing diameter helps because the smaller tubing is too restrictive of air. So yes, that is quite a possibility. So I would say that person is on to something. They need to pay attention to not only pressure but airflow. So yes, I agree. Fact-ish. So, okay, great. Thanks for the question. I appreciate those. It tells me we're definitely talking about something that someone's interested in. Okay, so the vacuum generators that we've talked about so far are what are called a decentralized system, meaning we're generating vacuum only where we need it. We don't have a big vacuum pump somewhere, just like a compressor somewhere, creating a bunch of low pressure being held in a tank. We're only generating the pressure where we need it, when we need it. The advantages of those is we're not spending a lot of money filling a tank that might be leaking everywhere. So it's relatively inexpensive, and you don't lose a lot of effectiveness going through a bunch of tubes and a bunch of pipes. The disadvantage is with these type of vacuum generators, you get a lot of noise at the point of use. That air, that coming out of the ejector, and that is not the most efficient use, but they're very effective, very often used. We used to use these at my former employers all the time because they were real easy to take care of, they were less expensive, and they were right where you needed them. All right, so now that we know how we're generating this low pressure, now we need to use a pressure sensor to make sure that we're getting the pressure that we require. So what a sensor does is it measures the difference between outside air pressure and the pressure inside the system, and then it compares the two and puts the number out on the screen. So in these are measuring kPa. So This particular type of sensor that we're showing here actually will change colors depending upon the set points. So in this case, apparently negative 84 kPa is not enough to turn the light green, whereas something higher than that would. So this pressure switch, one of the outputs would be sending a signal back to the PLC as well, saying, hey, something's wrong out here. We need to either stop or send somebody, or depends on whatever the output is. So when I say PLC, what I mean by that is the programmable logic controller. That's the brains. That's the controller of the big machine. And it receives signals from those pressure switches to know, are we within ranges or are we not? So not only do these pressure switches have visual indications, but they have external indications, like I said, where we wire things up to the PLC. Now, there are different types of wiring setups. A few of them I've mentioned here, NPN, PNP, hysteresis, using with auto switches and so on. We do have other webinars that cover that material, so if you need some more information on that, maybe we can get access to some of those recordings for you, so let us know. Now, the way you apply these things is you want to have the switch relatively close to the cups, because the pressure at the cups is the pressure at which you are functioning or failing in picking up the workpiece. Now, you're not always going to have the pressure switch right at the cups, but if it's close, that's the main thing. So this particular type of pressure switch simply has a little potentiometer on it, and so that you get the system so that it's working, and then you turn the switch until the light comes on. If the light comes on, that means it sends a good signal back to the PLC. Real simple, doesn't have a visual indicator, just what all you need is all you need, and so this one is just as simple as you can get. So I mentioned briefly that you should try to have the vacuum side as short as possible, meaning the side from the switch and from the ejector to the cup. Because, as I mentioned earlier, the longer the hose is, the more resistance you have to flow, and the lower pressure you'll have at the cup. So you want to try to keep these relatively short. And when I say relatively, I mean nothing like 3-4 feet, because you really see some pretty serious degradation in capability. And you'll get pressure losses. And the final thing is you'll get a false switch indicator, which means, let's say if I have my switch too close to my ejector, the switch may be reading a much lower pressure differential here, but that's not the same as at the cup. And so the switch says, yeah, we're good, let's go. But the cup really isn't where it needs to be, and as something moves, the cup could actually lose the workpiece. So try to talk to your customers and have them put the ejector and the switch as close to the cup as possible. Again, it doesn't have to be right on top of it, but try to get it as close as you can. All right, leaks. Now, some will say every pneumatic system has leaks to them, and there's some truth to that, but the goal is to try to get rid of as many of them as possible. Now, in some vacuum applications, there is no way possible to get rid of the leaks, because depending on the material you're trying to pick up, it's going to leak. Like, for example, cardboard. If you're picking up cardboard boxes, it's going to leak. Air is permeable through cardboard, or if you have something that has an irregular surface, there's just no way to make a complete seal. So even in a perfect world, there are some setups where you're going to have leaks through a vacuum. And that's fine. That's not a problem if you make up for the leakage. And what the deal is there is you've got to have enough flow to allow that air to leak, and enough to hold on to the part as strongly as you need it to be. So depending upon the different type of material, the work pieces that you're trying to pick up, you choose the pads accordingly. You can choose them with a more rigid or a higher durometer rating, like a fluoropolymer type cup, or you can get a silicone rubber, which is very flexible, which is good for some irregular shapes, but maybe doesn't wear as well as the harder one. So time needs to be spent matching the workpiece as best you can to the cups. And again, that's a whole nother long discussion on how to do that for sure. So in class, what we try to do here at SMC is we actually use a bunch of different workpieces, and then we try a different type of pads. Like this one is the harder fluoropolymer. This is the rubber, silicone rubber. These are NBR, and even different shapes, the bellows type, the flat type, the rib type, so on, conical back there. And then we do some measurements. You know, what happens when I put the flat one onto the ping pong ball? Does that lift? How about the silicone rubber? Does it do okay with the golf ball, or does it require something higher in durometer rating? So as you put these two things together, the cup that you've chosen along with the part, you then hook them together and you turn on the vacuum ejector and you do a test. Do I get any leaks or don't I? How you know whether you're getting leaks is you find one of these flow characteristic charts of the particular ejector that you're using. So here I chose to use our ZH ejector. I hooked it up with a vacuum pad and put a pressure gauge in between. And what you do is you put the cup that you're using and try to get a hold of the workpiece, and you turn on the ejector, meaning you send it positive pressure air, in this case at 4.5 megapascals, which is somewhere around 668-ish PSI. And under normal circumstances, if everything grabs a hold and there's no leaks, I should actually be generating somewhere around negative 90 kPa. But if I'm only generating, my low pressure switch is only showing something around 50, negative 52 or 3 or something, I then can go straight across this chart until I hit that diagonal line, and then I come down, and that tells me that I'm leaking about 8 liters per minute of air, because I'm never reaching my full pressure differential. If there was no leak, you would see those two things pushed together completely flat, and you would hear no leakage at all, and that would be all the way up here to negative 90 something. But as a result of the pressure never getting that high, I can determine how much leakage I have. That's with any ejector, that's with any pad, any workpiece, so long as you have this chart for the right ejector. Each ejector is a little different, so make sure you're using the right pad. So what that tells us, if I have 8 liters per minute of leakage, I better make sure that I've got an ejector that can handle at least twice that. So maybe one of those single stage ejectors maybe isn't the best use here, because I'm leaking. This is going to take quite a bit of time. So maybe this ZH10 isn't my best choice. Maybe I should try something else. So for an example of what happens to pressure when you have a leak, I used with our training equipment, we've had access to some of these simulation cells, and in the past we had this one that had these 4 cups or pads that would come down and grab a hold of this piece. Then the vacuum would be generated, the pads and the workpiece would be pushed together, and then it could lift it up. So with 4 pads making good contact and there was no leakage here, because everything was lined up perfectly, we could generate about negative 84 kPa or about negative 12 PSI. But if I had one of them that I intentionally made it be a little off-center, so one of the pads was leaking, the other 3 were making really good contact, this is actually the pressure reading. This is a picture of the pressure reading I got, which was negative 3.4 kPa, which is not even half a PSI. So that's not going to pick this thing up at all. So the leakage there is so bad that the pressure dropped so low that I wouldn't even be able to pick that up. So here's a picture of kind of the setup here. Here's my air pressure coming in. This is my ejector. Okay, so the air pressure is going through the ejector, generating low pressure. There's a filter here. I'll discuss what these things are in a minute. And here's the pads. Okay, these boxes are the switches, the gauges. So there's only 3 here, but let's say there were 4. So two of these pads were making really good contact, but this other one wasn't. And so as a result, I lost pressure everywhere. So what you can do, if you want to keep that from being quite as bad a problem, there's a couple options. The most basic is to put what's called a flow control in these lines. That's what this symbol is, these 2 parentheses with an arrow going through them. What that flow control does is that throttles down the air, which is going in to make up against the low pressure inside the ejector. And what that accomplishes is that if one of these pads doesn't make a good contact, it slows down the air that comes in and tries to make up this low pressure. So the pressure in the other pad still stays higher than it would have, like in my example. Now, the downside of that is with these air throttles, you're slowing down the airflow through the whole system. And what does that do? What did I say earlier the flow in the vacuum system was about? It was about how fast the pads can adsorb to the workpiece. So that'll actually slow your adsorption, your grab and hold time with those flow controls. Another option is what's called a vacuum saving valve. We have one of those that what it does is as long as the air doesn't flow through very quickly, then the vacuum saving valve stays open. But if one of these misses contact and the air starts flying through it very quickly, that vacuum saving valve will actually close. So instead of it being a throttle, it would actually close like a check valve here, so that this pathway would not allow air in, and now I have what would be the equivalent of 3 good pads. So I wouldn't lose pressure in my system, so there'll be the high pressure in these other pads, which may still have enough power to pick up the workpiece. So that's another option. So if you have a customer who's having some alignment issues and as a result the pads aren't hitting and they can't seem to get them aligned, those are a couple solutions for them. The basic, less functional, but works, is to throttle these with a needle valve. The better solution is the vacuum saving valve, which only throttles the air when there is a misalignment. It doesn't throttle it all the time. So to give an example, I didn't have a vacuum saving valve handy, but I did have some needle valves. So I did the same as I did before. Here's my 4 pads with good contact. Again, that's the generation of low pressure that I had, negative 84.7 kPa, or about 12 psi. Then I did the same thing. I made one of the pads so that it didn't make good contact, but I had some speed controls in the lines. And notice I got almost negative 6 psi this time. I still didn't get the same amount of low pressure I had before, but I had a much better shot at actually holding the part with, instead of 0.5 psi, I had negative 6 psi. And when you size these things, which is a whole nother webinar to size all these parts, you need to put what's called a safety factor in there. And usually the safety factor is somewhere between 2 to 4 times, even 8 times, where you've got enough low pressure in here that if it got cut by 1/8, it still would pick it up. And so in this case, I only lost pressure by about 1/2. And so there was plenty of safety factor. It still worked. So trying to show you a real world example of how this stuff works. So the question we had, yes ma'am.
Oh, just real quickly, we have a question for what is the commercial name of foam used for the cups?
Foam? Well, the ones we sell them as rubber. You'll hear it called BUNA or NBR. Then if you, we have other materials like we call it a fluoropolymer, which is similar to a Viton type. That's harder, higher durometer. Then we have silicone rubber, which is the more flexible. Doesn't wear quite as well, but it's more flexible. Then if you need like a non-marking cup, we have, it's basically a BUNA with a PEEK insert, polyethylene something, I don't remember. I'd have to look up what PEEK stands for. But that PEEK is less apt to mark whatever the pad is touching when it picks it up. So I would refer you, if you want to see what the entire product line is, we have some pad books, the ZP catalogs, which will have not only a list of all the different types of materials, but what are they best at. Like the BUNA is better under this circumstance and that circumstance, but maybe the silicone rubber is better in these other ones and not so good at this one, and then so on and so forth. So I would refer you to that. Hopefully that helps a little bit. Okay, again, thank you for the questions. I appreciate those. So back to that, that first question we had to show you the chart. If you'll notice, this is again is a ZH style, but this really applies to any vacuum ejector, not just this particular one. If you'll notice, as we supply air pressure to it, that's on the bottom. Our catalogs are always in MPa seams. So 0.1 MPa is roughly 15 psi. 0.2 then would be 30, 45, 60, and then somewhere between 60 and 75. If you'll notice, at that point, as I'm supplying positive pressure to that ejector, you notice that my negative pressure starts to degrade. I give it more and more pressure, but I'm losing actually at some point performance. So there is a point, and it's not always the same, but roughly at about 0.45 MPa or roughly 67 psi. Please look at the catalogs to find out exactly what it is for each ejector you might buy. But there is a limit. So cranking up more power will actually cause you problems and won't help you any. So that person was thinking ahead when they asked the question, because it does matter. All right, the agenda for today was to talk about vacuum generation. How does it work? Why does it work? And so on. I talked a little bit about pressure sensors, some of the options in general of different types of pressure sensors, and then leakage. How's it caused? Well, what does it cause in general? That it slows you down, you lose pressure, and so on and so forth. So that was our agenda for the day. I think we've covered at least most of that. I want to thank everyone for attending. I want to thank Bras for allowing us to help with this. I'm the National Training Manager. I was very honored to get the opportunity to present to the folks that are here. I'd appreciate any feedback or examples of how you use some of this information, or even maybe some ideas for future webinars. The best email address is training@smcusa.com, and that'll get that information to me, and we can make these better for the next time. So with that, and barring any future questions that may happen in the next few minutes, I will turn it back over to Miss Amanda, and thank you all for your time.
All right, thank you, John. Thanks to everyone for attending, and thank you for the questions throughout the webinar. We don't have any further questions in the queue, John, so I think we'll go ahead and just wrap this webinar up. So like I said, thanks to John for presenting this information on vacuum technology. It was a great presentation to give us a general understanding of the vacuum technology and the different components and examples that are within it. We would especially like to thank Bras for giving us this opportunity. And for any questions, feel free to contact Bras directly, and they can help you out with any of your SMC product needs. So thanks again for everyone for joining us. Have a nice day.
Thank you.